Hello everyone, welcome to week 4 module 2 video presentation on feature engineering and introduction features. So in this video I will walk you through the process of creating introduction features and applying polynomial features in linear regression, evaluating their impact on model regression and on module performance, and I'll also discuss the trade-off of using higher degree polynomial features and then reflect on the importance in machine learning. So the main topics I will cover today are understanding interaction features, creating polynomial features of different degrees, training and evaluating linear regression models, observing the impact of interaction features on model performance, and then reflecting on challenges, benefits, and insight from these exercises. So once we have imported our libraries, imported our libraries in here, we have tried to read the datasets, which is from Kaggle over here. So first, this is how our dataset looks like. You notice that there's a space in here. That means our data is not clean. So we have tried to clean the data. That means there is no space in here. So that means our data is clean. So in this, we started with active class exercise 1, which is understanding the process of creating interaction features. So the steps are one, feature selection. That means choosing the original features that we want to interact, uh, generate interactions. That means creating new features by combining pairs of interactions. This can be through multiplication or using polynomial features. Integrate into the data sets. That means adding these interaction terms as new columns, and then all at the end we try to train the model with the updated data sets. We can catch the interaction terms, and then it can be used to train a model to capture more complex relationship. So by doing this, we allow even a linear model to capture non-linear interaction between variables. So, for example, even if we have different degrees, we can work with it. That means the polynomials or interactions are either higher in polynomials or lower. So we're trying to work on that today. So polynomial features allows us to systematically capture interaction in a near patterns. So that means degree 2 quadratic, which is the interaction features that captures pairwise interaction and the simple nonlinear relationship, and when the degree equals to 3 or more, or that means a higher degree, captures a more complex relationship, but we also risk overfitting. So it's important to balance model complexity. For example, higher degree polynomial features increases dimensionality, risk computational cost, and can reduce the ability to interpret and analyze. So in practice, we often start with degree 2 to explore nonlinear effects without drastically increasing model complexity. For example, we have done in here, and then we have done on x1, x2, and then we also have done it on x3. So before creating interaction features, let's look at our dataset. So the original dataset has 39,644 rows. You can also look at it in here on the Kaggle page, and it also has 61 columns, but we try to look only at 17 of the columns, which is content-based features. These features in here. So after applying the polynomial features of degree 2, the data set expands to 170 degrees. So from 17 to 117 features. So here's a breakdown. So that means 17 original features, for example, n tokens total number of images, average positive polarity, and then 17 squared time, for example, n tokens title is squared, and then number of images is squared, and then plus 136 pairwise interaction, that is the n tokens title times n images, and then another example is the number of hrefs times average positive polarity. So if you combine all of that, I add them together, that's going to give us a total of 170 features. That's going to be our degree 2 or quadratic polynomial features. So if you move down to the model regression, we split the data set into training and testing set using train test split. So we train two linear regression models. One is the singleton, and then the other one is pairwise interaction. The singleton features is the original 17 features, and then the pairwise features is the expanded 170 features. So we evaluate the model using the R squared score. So the result we get is 0.0924 0.00924 for x1, and then 0.01132 for x2. So although both are solo, adding interaction terms improve the model slightly. This suggests that some relationship between pairs of features contribute more to predicting the target than individual features alone. So analyzing the R-squared, we observe that both the singleton and pairwise features have weak predictive power, indicating by score close to zeros. The slight improvement from the interaction feature highlights minor nonlinear relationship captured by the polynomial features. So overall, the features in this data sets are not strongly informative for predicting the target variable, but the interaction feature shows the potential for improvement. For our above and beyond tasks, we applied degree equals to 3 with polynomial feature, which expanded the feature set from 17 to 170 to 1139 with the same formula we used above in here for and when our degrees equals to for the quadratic one. So after training a linear regression model with these features, the R squared dropped to 0.0416. It's also shown in here, that's negative, and it shows that there is overfitting and it's a poor generalization. So this is gonna show us this shows that's a key trade-off. While higher degrees polynomial features can model complex interaction, they can also increase model complexity, computational cost, and the risk of overfitting, as we saw from the interaction polynomial feature interaction when the degrees equals to 3. So let's summarize the pros and cons of polynomial features. The pros are that it captures nonlinear relationship, and then it allows linear models to model complex interaction, and it can also slightly improve performance if true relationships are nonlinear. And the cons are that it increases dimensionality, higher computational costs, reduce interpretability, and risk of overfitting, especially with higher degree polynomials. So from the exercise, we learned that feature qualities matters more than quantity, so selecting the relevant interaction improves model performance. wisely, balancing complexity and interpretability. Polynomial features help, but overdoing them can harm the model. And then interaction features enhances linear models, and they capture relations that linear terms alone cannot. So overall, careful feature engineering is crucial for building accurate and efficient and interpretable machine learning models. So to continue with to conclude week 4 active class, we have learned the importance of interaction and polynomial features. We practice creating these features, observed the effects on model performance, and reflected on the trade-offs involved. So that's the end